Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
What if I told you that one of the most powerful industrial materials comes from just burning rocks? Yes, from steel plants to water treatment, from construction to chemical industries, quicklime is everywhere. It's the hidden engine of modern infrastructure, yet most people have no idea how it's made. But how do we transform ordinary limestone into this highly reactive powerhouse? Today, we're going on a 5-minute deep dive into the science, engineering, and massive industrial scale of lime. It all starts millions of years ago, under ancient oceans where calcium carbonate deposits formed. Everything begins with limestone, primarily made of calcium carbonate, or CaCO₃. For industrial use, we need purity. High-quality limestone contains 90 to 98% carbonate. Traces of silica, alumina, and iron can change the lime's behavior in the kiln. In the quarry, precision drilling and blasting break the rock into manageable pieces. Huge excavators then move the raw stone to the primary crushers. This initial crushing reduces boulders to sizes easier for the factory to process. Why does size matter? Because in the kiln, heat must penetrate to the core of every stone. Now, we enter the heart of the plant, the calcination process. This is where stone becomes fire. The core reaction, calcium carbonate plus heat splits into calcium oxide and carbon dioxide. This requires temperatures between 900 and 1100 degrees Celsius. That's hot enough to melt aluminum. In large plants, we use rotary kilns. These long, inclined cylinders rotate slowly as stone moves through. They are designed for high capacity and continuous operation, producing hundreds of tons per day. Alternatively, vertical shaft kilns are used for their incredible energy efficiency. Critical control factors are temperature and residence time, how long the stone stays in the heat. Overburn it and you get dead lime, which has very low reactivity. It's essentially ruined. Underburn it and the stone doesn't convert fully, leaving a core of unreacted limestone. Once calcination ends, the lime must be cooled instantly to lock in its reactive properties. Fast cooling prevents the lime from reabsorbing carbon dioxide from the air. The final quicklime is screened, sized, and moved into moisture-proof storage silos. And remember, quicklime reacts violently with water. One drop can start a fire. This leads us to the next stage, slaking. When we intentionally add water, we create hydrated lime. The chemical formula changes to calcium hydroxide, releasing an enormous amount of heat. This exothermic reaction is so powerful it can actually boil the water used in the process. Why do we make all this? In the steel industry, lime acts as a flux to remove impurities from molten iron. It forms a slag that floats on top, leaving behind pure, high-strength steel for our buildings. In water treatment, hydrated lime regulates pH levels and helps remove heavy metals and pathogens. In construction, it's a key ingredient in mortar and plaster, providing breathability and durability. It even protects our environment by scrubbing sulfur dioxide from power plant exhaust gases. But lime's reach extends far beyond industry. In agriculture, it's used to balance soil pH levels. By neutralizing acidity, it unlocks essential nutrients for crops, significantly increasing global food security. The paper industry also relies on lime for chemical recovery and as a filler for brighter, smoother paper. It's even vital in mining, helping separate valuable minerals from ore in flotation processes. But working with lime requires extreme caution. It is highly caustic and can cause severe chemical burns. The dust is a major inhalation risk. High-tech ventilation systems are critical in every modern plant. As we look to the future, the industry is racing to reduce its carbon footprint. Engineers are developing systems to capture the CO2 released during calcination and store it safely. Waste heat recovery systems are now turning the kiln's massive energy into electricity to power the plant. From ancient stone to high-tech sustainability, lime continues to shape our industrial world. It is a material that is simple in its origin, but incredibly complex in its contribution to humanity. Thank you for joining us for this deep dive. If you learned something new, hit that like button and subscribe. I'm the narrator 1PX35, and we'll see you in the next engineering secret from Simple Gyan. Goodbye.